Hello everybody, I just wanted to, in this video, do a little background on the classical wave equation and where it comes from. So what you've seen in the past is that classical waves have some functional form like this. Where we have both a wave in time and space. But where does that come from? And so I wanted to go through a little bit, just a very rough derivation of the picture that leads to it. And so we can imagine, we want to look at waves on a string. And we can break the string up into a bunch of springs and masses, and then basically take a limit as the number of springs and masses becomes very large and becomes a continuous object. So we model it sort of like this. We have a mass, and then we have a little spring, and we have another mass, and a little spring, and another mass, and this just goes on. So we have a bunch of little masses connected by springs, and we really, the equation that we'll get this solution from is really just Newton's laws. We want to look at what are the forces on this particular mass and add them up. So first we just write down actually the right-hand side of Newton's laws. We basically, the sum of all forces is equal to the mass times the acceleration. Now here we're imagining things waving up and down. So we're imagining these masses are moving up and down, and we're really just going to worry about the vertical component of the spring force. We're going to sort of pretend that the horizontal part isn't doing anything interesting for this. We're just going to treat these springs as acting vertically. So what we have then is on the right side of the equation, instead of acceleration, we're just going to write down basically the definition of acceleration. It's moving up and down, so it's really the second derivative of y with respect to time. On the left side, what are the two forces? Well, each mass is connected to two of its neighbors. So it's got two spring forces, and it's got one from the left, one from the right. And really, because it's connected to its neighbors, what matters isn't really the absolute position y, but what matters is where is it compared to its neighbor. It's above its neighbor, it gets pulled down. It's below its neighbor, it gets pulled back up. So what contributes to each force is not the position y, but its difference from the position of the previous mass or the next mass. So it's really the change in position with respect to x. So it's a derivative, really. But in fact, there's two of these springs, and if the change is the same from one to the next, so for example, you have something like this, well, one pulls up, the other pulls down, they balance out, the net force is zero. And so it's not enough to just have a change in position along the x direction. You have to have a change in the change, which is really a second derivative. So you have to have something like this, where the slope is sort of different from one to the next. Then there's a net force. And so what goes on the left-hand side of this equation is really some spring constant, and we use k too much here. I've already used k here, but I'll call this k. This is a spring constant k. It's not the same as this wave number k up here. But we've got whatever describes the strength of the spring, a spring constant, and then we have the second derivative of y with respect to x. And so this is the classic differential equation for a wave. And it shows up in a lot of places in physics. You get a similar equation for electromagnetic fields and electromagnetism. You can generalize this to multiple dimensions. You can see it all over time. It's just a classically well-known wave equation. And actually, usually what people do is they combine these constant terms, or they're not always constant, but these coefficients in front, you put them together. Different people write it different ways. Let's see, d squared y dx squared equals, sorry, let me clean this up a bit. D squared y dx squared equals d squared y dt squared. And so you have this something like a spring constant over something like a mass. What are the units there? Well, y has the same units both sides. The difference is this x and the t. So if you look at this a little bit, you can convince yourself that this thing over here, this combo, has to have units of distance squared over time squared, or a velocity squared. And in fact, that velocity is the sound speed of the wave. It's basically the speed that the wave propagates. And so the most common way that you see this wave equation written is something like this, where you call this CS, that's the sound speed, and d squared y dx squared equals d squared y t squared. And that's the differential equation that leads to a classical wave solution that I wrote up at the top there. So that's really where that comes from. And so the question for us next in quantum mechanics is going to be, well, if all matter is somehow a wave in quantum mechanics, the question is going to be, what is the wave equation? Is it that? Is that going to work? Hint, no. But what is our wave equation? And that's what we want to find and then solve to get our solutions for the quantum mechanics.